we can see a Kubernetes cluster is made up of one single master and a fixed number of nodes. And the keyword here is fixed number of nodes, which is translate into finite amount of computing resource for Kubernetes to utilize for pod-based scaling. Well, given this architecture, we should be asking the question, what happens if the configured numbers of nodes is maxed out in terms of its ability to provision pods, right? I mean, with a fixed number of nodes, there's an obvious upper limit to the number of pods that can be provisioned. Well, fortunately for us, GCP has implemented another scaling feature that will go hand in hand with HPA to overcome this bottleneck. And it's called Cluster AutoScaler. As its name implies, it is responsible for automatically adding node or nodes to a Kubernetes cluster when the load demand has exceeded its current size for node pool. And we will demonstrate how this feature can be implemented in GCP. As a prerequisite though, I will assume the audience already have some basic understanding of Kubernetes and its architecture. We will start by provision a brand new Kubernetes cluster using Google Cloud Platform CLI, G-Cloud. Then I will create a deployment using a .NET Core image that has a dead simple C# function that is designed to generate high CPU utilization. And this is what the code looks like. By the way, all the code artifacts used in this video will be posted on the GitHub repo listed below, so you can review it at your leisure. After that, we'll utilize another pre-existing pod to hit the first pod repeatedly in order to kick up its system load. During all this, we will observe how GCP's implementation of Kubernetes HPA and Cluster AutoScaler works hand in hand in order to handle the scaling up and down of resources. All right, let's get started. First thing we're going to have to do is to create a Kubernetes cluster by issuing this command, the gcloud command. And I want to point out a couple of things about this command. First is a beta. This is still a beta feature as of the time of this recording. And then the other thing is to make sure that you issue this parameter enable autoscaling, as this is the parameter that would enable the cluster autoscaler feature to work. And we issue this command, and it's going to take a few minutes for it to create the cluster. All right, the cluster is created, and we can verify that by going to the portal and see that indeed the cluster is created along with another cluster that I've created previously that we will use later on. Now we need to connect to this cluster from our command prompt. Easiest way to do that is to click the connect button. That will give us the gcloud command that we can use to connect to this cluster. We copy that guy, paste it here, issue it, and we're connected. Now that we have created a cluster, the next thing we have to do is to create a deployment using the kubectl run command that will use an image that contains the C# function I have shown earlier. Next, we have to create a service of type load balancer to have the pods to be externally accessible. And finally, we have to create the horizontal pod autoscaling by issuing this command. Note the parameter, the CPU-% equal 50. This will tell Kubernetes that we want to keep the observed CPU level to be around 50%. If not, then it should create more pods to handle the load. in order to keep the threshold around 50%. And we can do a quick check on the CPU level. And as you can see, there's 0% as there's nothing is hitting our pods. Next, we want to know the address, the load balancer address that was assigned. And we can do that by using the get service command. And we can see that the assigned IP address is this. And we can do a quick test. As you can see, the calc function is called by going to this route. As I mentioned in the overview, we will simulate the load generation by using another pod cluster so that we have a clean separation between the load generations and the load consumption. So now we do that by switching to the other cluster I have created prior to this recording. And copying this command. Well, actually, we need to run this in a separate VM in the cloud. Otherwise, CTO will get very confused about which cluster that it is going against. So let's do that. And in this cluster, we'll just create a very simple. We will just create a very simple pod using the busybox image and call it load generator. And we'll just have it hit the low consumption cluster. As you can see, it's calling the function. Okay, now that we have all the background setup out of the way, the fun parts begin. Let's do a quick check on how our pods are doing. And as you can see, our load generator is kicking up quite a load storm on our pods. And if we do a quick check on pods, we see that Kubernetes already trying to spread the load by spinning up 3 additional pods. And if we do a check on the number of nodes, and it remains at 2. And this is the number we specify in our initial cluster creation command, which had a minimum nodes of 2. So after 4 pods are created, you can kind of see the CPU are starting to go down a little bit. As expected. However, it's still way about the 50% threshold that we specify. Well, since the CPU utilization is higher than threshold, one would expect Kubernetes to continue to spin up more pods to handle the load. And as you can see, it has doubled again to 8 replicas or 8 pods. And we can certainly verify that by doing a CTL get pods, and there are 8. And let's see how many nodes we have at this point. Aha! So you can see, since we are spinning up more pods, and with the 2 nodes, that was the initial size of our cluster. The cluster autoscaler has kicked in and starting to spin up more cluster nodes to handle the pod creation. That's all fine and dandy, but at 133, it's still above what we specified of the 50% threshold. So one would expect in a few minutes, Kubernetes will try to once again double the number of pods in order to lower the CPU. So there it is. It doubled again to 16. And if we go to the dashboard, the Kubernetes user interface, you can see the error messages that it has insufficient CPU, showing that the number of nodes that it's allocated at this point is not enough to fit the demand of the additional pods that it's trying to create. And so let's do a quick check on the number of nodes that's currently available. Aha! So it actually went ahead and created an additional node that will pretty soon kick in and let Kubernetes fulfill the needs to create the additional pods. With the additional cluster node being created, we can go back to the dashboard and we can see all the pods, 16 of them are created successfully and is running. And if we go back to console and do a get HPA to do a quick check on where we're at as far as the CPU, we can see we're getting very close to the targets we specify, which is at 50%. Well, with 16 pods, it wasn't enough to get to the threshold of what we're looking for, which is 50%. So Kubernetes is smart enough to add 2 more to the pod, and after a while, hopefully that will meet the threshold that we specify. And there you have it. With 18 pods, it was able to get below what our threshold. And at this point, I think we can end our demo. And we can do it and stop our load generator first. And with the load being stopped, Kubernetes is going to be smart enough and stop killing off pods as they are not needed anymore. And at some point, it would spin down the nodes as well to save resources. So this is great for resource saving, cost saving, as Kubernetes is really helping you to right-size the number of resource, both in terms of pods and nodes, in terms of dynamically meeting the load. And there you have it. We are back down to 1 again, given that there is nothing hitting our pods. And Kubernetes has done the right thing in terms of shutting the number of pods down. So this will conclude our demo. I hope it was educational and informative. Until next time, see you. Bye-bye.